All right, so now we begin Unit C, which is our third unit out of 4 units, and we begin with uniform circular motion, which is lesson 19. Now, the unit itself is called uniform circular motion, but this is where we really introduce the terminology and the specific key pieces that are really necessary for this unit. And then going forward, we're just going to work more on specifying the different types of uniform circular motion and what that can look like, including things like orbits and satellites, vertical circular motion, and we're going to see more and more and more throughout the unit. And then we'll kind of go into energetics past that point. But for now, let's really build those fundamentals that we're going to need for Unit C, or our third unit. Starting off with the first concept right away, in class, what we would have done is taken a look at our acceleration formula that's given to us on the formula sheet. And that's this piece here. According to Newton's second law, we know that an unbalanced force or a force imbalance causes some sort of acceleration. And so we can give this equation here. Now, with a simple rewrite, if you want to arrow over here, we can write this as the following. F, or the force, is equal to mass times the acceleration. So that would be another way to see this. Now, that's the more common way, because often what we called this is that if we wrote it as F equals ma, or force equals a mass times acceleration, from our previous unit dynamics, we typically said that this was our F net, which was equal to mass times acceleration. And in things like pulleys and general systems, we always also called this mass of the system times acceleration of the system. But I mean, just generally and very broadly, if we have some sort of net and unbalanced force, we know that there is an overall acceleration, or that there is some sort of net force happening. Now, taking that concept and applying it into a very simple example that we can work with here, suppose we have the following. If I have some sort of soccer ball, I'm going to consider that this ball here. And let's say it's moving across the field to the right. And then some soccer player comes and they kick it and they give it some force from behind, which then accelerates the ball and gives it this new velocity. Well, what we're going to notice is that the overall speed, or the overall velocity, changed, aka it increased, as there was a force applied. And we know that anytime a force is applied, we should get some sort of change in that overall speed. But in this case, we're not changing the direction. We're just kicking it in the exact same direction. Now, what if we look at this slightly differently and we say, what if I apply the force at some sort of angle? Let's call it a 10-degree angle, and it's being applied to the soccer ball that's still going across the field to the right. Well, what we're going to notice is that if I apply a force, or a net force, on an angle to some object that already has some sort of velocity in a given direction, what this is also going to do is this is going to change not only the speed, but it's also going to change the direction. And hopefully you see that right here. We have a certain magnitude to start, we have a certain magnitude at the end, where the two components that changed were, first of all, a change in direction. So I'm going to put delta direction, or change in direction scientifically. And then we also saw that the speed, or the given velocity, increased. So if you want to put like 1 and 2, these are the two factors that are affected by some sort of force being applied at some sort of angle here. Now, we know from both of these conditions, acceleration occurred. And that's where we go into this line that is very, very critical for us going forward into this unit. And it's this piece here. A change in either speed and or direction is an acceleration. So according to those first two examples that we just dealt with, or those first concepts, that would 100% be true. And I would definitely star this in your notes. This is one of those concepts where you don't want to just skip over, because it is part of the definition that helps us form uniform circular motion. Is either a change in speed and or a change in direction is this acceleration. Now, taking this a step further, suppose we have some sort of example to the right here where we have some sort of circular motion going on. And this circular motion, we could consider a ball on a string. We could consider it realistically anything that would go in this circular path. But I like to say it's a ball on a string going around and around. The major thing we want to highlight from here is the following. A net force that is perpendicular, or 90 degrees to the object's motion, does not affect the speed, it only affects the direction. And so what that means is the following. If I have this ball and it's going around in the clockwise direction, and I call that some sort of speed, and it's forming this 90-degree angle right in here, and I should maybe draw that in the way that you would see it in mathematics. We would see this as 90 degrees. And then we look at this and we're like, the force, or the net force, wants to bring this object down towards the middle. So we call this in this unit our centripetal force. And don't worry, we're going to get there. So it may be a little bit early. But the major thing I want to show you visually here is that if my speed, or this outer speed, this tangential speed, is at a 90-degree angle to that given force, we consider this to be only changing the direction. And what that means is that as I go around the circle, this is rapidly going to be changing its tangent velocity direction every couple milliseconds or every time we look at it from a new framework of a certain specific point on that circle. Now, therefore, if we have a perpendicular force that is constantly applied, the constant speed will have some sort of continual change in direction, but a consistent speed. And thus, we get uniform circular motion. Hugely critical, hugely critical. I would just highlight this, be like, this defines what uniform circular motion is, or UCM is this paragraph here. Now, with this one, uniform circular motion involves an object moving in a circle at a constant speed. Notice that the speed is constant and the velocity, i.e. the direction, is constantly changing. Uniform circular motion is accomplished by applying this force at a 90-degree angle to the original motion of the object. So consistent applied force all the way around. Now let's take a look at this even closer, because realistically, this paragraph does enough, and it does it justice, quite frankly, but we really want to visualize what this actually looks like. So let's flip over to our next page and take a look. So here is a ball and a string that are attached, and it's rotating around in the counterclockwise direction. So what I would do right away is on this diagram, put a center dot in, because it's going to be really popular for us to do that in lessons 19, 20, and 21. It's going to be really important to do that. Now, what we have is we have this overall FC, or what we were going to come to know as the centripetal force, a center-seeking force that wants to bring the object towards the middle, or not necessarily towards the middle, but what it's going to do is this net force is going to continuously change this given speed's direction, aka changing the direction of this overall velocity vector. Now, on the outside here, or on the inside, first and foremost, I just want you to label FC, FC, and FC. And the number one thing you should notice is that all of these FCs, or all of these center-seeking centripetal forces, are equal in magnitude. So you want to say equal magnitude. The other thing you may want to mention is that our FC is the net force. And this is what we're going to talk about moving forward a lot, is that when we have this centripetal force, it's actually the net force, because as we're going to come to learn in lesson 19, we can actually put together forces that give us some summation that form this FC, meaning it's the sum of forces that form this FC, or the center-seeking force. Therefore, we can define it as the F net. The other thing I want you to do on this diagram is label this as speed, speed, and speed. Now, these speeds are continuously changing direction, aka there is acceleration. That was one of our factors that formed acceleration. We said it can either change in overall speed, it can change in its magnitude, meaning it can go from like 5 meters a second to 10 meters a second, or it can change direction. So it doesn't have to necessarily be that the magnitude of this speed is changing. Rather, it can just be the direction that causes acceleration. And we know that any sort of F net, or any sort of imbalance in forces, by second law, if the FC is the only force and there's a force imbalance towards the center, that means that we have some sort of second law, and that there must be some sort of acceleration. So we look at this, and this FC is going to be contributing to that constantly changing velocity as we go around. And just to put it in perspective, we have 1 point on the circle, 2 point, 3 points, and 4 points, in which all of these have the same FC, which is that center-seeking force, but different direction in terms of their speed. So very, very critical. Now, something to note here, and something you may want to highlight for yourself, is this. If the centripetal force is removed and the ball were to move at that constant velocity, it would shoot off in the tangent in which it was removed. Meaning, if I look at this circle here, and suppose, let's say, it's going around the circle, and we look at this key interval. If I decide to cut the string here, or let's say this center-seeking force is cut, what would happen is that the ball would shoot off in this direction, or in the tangent velocity at that instantaneous moment. So similarly here, let's say I was looking here, and I cut the FC, or I cut that center-seeking force, this ball would shoot out this way, directly on its path, or directly on that tangential velocity, or that tangential overall projected motion, if you really want to call it that. Now, something really important here is we want to take a look at the sources of centripetal force. And this is going to be really important to really key in on, and not treat it like we're talking about a first law problem, but rather that we're trying to classify the force of FC as different things. So first and foremost, we're going to highlight this piece here. Circular motion is the effect of an unbalanced centripetal force acting at 90 degrees to the velocity of the object, as mentioned on first page. The unbalanced force is the cause of the circular motion, meaning the unbalanced force causes that directional change in the given speed on the peripheral. Now, we can actually classify our FC in the following ways. And here's what I would like you to highlight in your notes. One classification is the tension. One classification is the force of friction. The other classification is the gravitational force. Now, what this simply means is that starting off with the first one, I can have tension be that force that is causing the object to maintain this circular balance. So, meaning I could look at a tennis ball on the end of a string and be twirling it around in a circle. What would happen is that I'm just continuously twirling this thing, where the tension is that FC trying to bring the object into this circular motion or this uniform circular pattern. We could also have something like a car that's going around an overpass or like an exit. And as they take the exit, they're going around the curve. And as they go around this curve, the friction is going to be that center seeking force that wants to keep them on the road and make sure that they don't slide off. What would happen is if, let's say, the conditions got icy and we couldn't have that friction, well, the car would just simply say, if this is the curve and the car is traveling on this trajectory, if the force of friction that is that center seeking force is removed, what would happen is the car would shoot out along the tangent in which it was at that instantaneous moment, or shoot along that 90-degree perpendicular trajectory that it was on. So this would be typically a car on some sort of exit. The last is gravitational force, and this is where we go into the classification that deals with lesson 21's material, which is orbits and satellites. So we may not cover a ton of gravitational force necessarily within this lesson and the next lesson, but we will see that very shortly. Now, again, what I would write here is that we can classify. These are all classifications of FC. So I'm going to write it like that. Classifications of FC. So what that means is I could even write this in the margin. If I want FC, it can either be written in terms of an FT, it can be written as an FF, or it can be written as an FG, just depending on the problem. Now, this is a really simplistic approach for this. So don't think that all problems will be solved like this, but in basic uniform circular motion, the centripetal force can be described using one of these forces, and we're going to see that throughout the practice problems. All right, now we flip our page here, and there's an important note to be made here because you're probably still thinking like, okay, we get that the F net is going towards the middle, so that makes sense that, there's some sort of acceleration. But then you're still thinking like, if the F net's going to the middle, why is it that we say that the acceleration is also going to the middle? Like that must have some sort of significance in terms of the general equation. Well, suppose we look at the following example here, and I mean, they do a good job in your notes of outlining it here, but what we're going to do is just go off to the side here and really piece this together for ourselves. So suppose we have some sort of moment in time on this overall circular motion pattern, and we consider two intervals. We consider at point A, which is here, and then point B, which is right here. Now, at these 2 points, they share the same speed magnitude. So we're not concerned about one having a greater speed than the other necessarily. What we are concerned about is the following though. By construction, we know that acceleration is equal to the change in velocity divided by the change in time. Now, if I expand this out, it's going to be velocity or final velocity minus initial velocity over the change in time. And I'm just going to simply rewrite this in a slightly different way. Vf plus the negative Vi over the change in time. And this is also equal to acceleration. Now, if you don't believe me, look at this very closely. We have a negative in the middle, positive and a negative, they form a negative. So we're just rewriting this in a way that satisfies a following condition. As defined here, acceleration equals the change of velocity over change in time. By tip to tail vector addition, if I put a positive VF in the positive direction, and then I take my negative VI, the magnitude, and by tip to tail vector addition, I add it from tip to tail, I get that we have some sort of change in velocity heading in this south or towards the middle direction. So I'm going to get change in velocity is this resultant. If you really wanted to, from our previous unit, we often called this the resultant vector, but in this case, it's defined as the change in V. The change in V is heading towards the center of the circle. So I really indicate this here, that this is our center of the circle right below. Center, and I should really rewrite it out like this: center of circle. There we go. Perfect. So if I was to look at this from above, our center of our circle would be like right here. But in the case of us doing tip to tail vector addition, we kind of lose that center of the circle. So I just want to indicate it goes there. Now, what does this also mean for us? If we know the change in velocity is heading towards the center of the circle, it must also be that our acceleration follows that same pattern. So if you wanted to, you could also say that acceleration heads down, and you could use some sort of arrow to represent that as well, because it is important to note that that change in velocity direction is where the acceleration is tending towards. So very, very important here. Now, let's just take a look at the overall situation to make sure that we have this all put together. Again, I wouldn't ask you on a test like prove why the centripetal acceleration goes towards the center of the circle. Like we're not in a proof-based course. We're not in a pure applied course. So we don't want to really necessarily go too much into the proofs, but of course it's important to understand where that derivation comes from, or roughly how we can conceptualize why acceleration and why, namely, the imbalance in force going towards the center causes this acceleration to go towards the center of the circle. Okay, and again, it's a center seeking force. So don't be surprised that on this circle, when we talk about uniform circular motion, we're going to have some sort of uniform force that is going to want to center seek or bring the object in this circular pattern. Okay, now flipping the page here, I just want to take a look at the equations. And throughout this unit, what you're going to notice is on the formula sheet, we have a couple variables, and namely a couple formulas that deal with things that are titled VC, or the centripetal speed. We also have AC, but we are definitely not given, and I know that they say this is on your formula sheet. It is not on your formula sheet. In fact, what we need to do is I want you to cross this out, and instead what we're going to do is all over top of this, and I'm just going to make that a touch neater, just to make sure. There we go, cross it out. No mistaking that this is on our formula sheet. I want you to write in the following thing here, because we're really going to tie a parallel to what's going on in this equation and how we can determine the force given this type of setup here, which will enable us to solve more problems. So first and foremost, I want you to write Fc is equal to mass times the centripetal acceleration. Now, the centripetal acceleration is that piece that is the center-seeking acceleration in this problem. Now, how did we draw a parallel from the first equation that we wrote out, Fc equals mac, to this new equation? Well, here's what I want you to do. Mass is in both equations, so we don't really need to hyper-focus on that. But what I do want you to see is that this v squared over r being equal to ac is on the formula sheet. In fact, when we say ac is equal to, there's two options on the formula sheet. One of those options is v squared over r. So that's where this piece is coming together. And that's why I said cross out that this equation is on your formula sheet. No, this specific equation isn't on your formula sheet. But what we do have on our formula sheet is mass times acceleration. We just now need to classify it under this new mass times the centripetal acceleration rather than just basic acceleration from the previous unit. Now, if we zoom out here, something to notice here is exactly this piece here, which it was just exactly discussed above. So don't feel like you have to rewrite anything or go into detail a lot, but I just want to really reemphasize that Newton's second law gives us this idea that a force is mass times acceleration. We reclassify it to an Fc, or a centripetal force, a center-seeking force, equals mass times the centripetal acceleration. And now, if I put these two things side by side, what I can figure out is that if Fc equals mac, and AC is specifically equal to this v squared over r from our formula sheet, then when I put these things side by side and I put them together, I'm going to notice that my masses can go away and that I get the equation that's on my formula sheet. For sure, I can confirm for you right now, this equation is on your formula sheet. However, this equation is not. So just being very specific with that, of the way to get from here to here is just multiply it by mass. Okay, next page here. Very important note as we go into our first practice problems. And in fact, this actually appears in two units. This is in Unit C and in Unit D. It's in both. Very, very critical. And the reason is because we use period and frequency a lot within this specific unit. But then when we start talking about waves and the properties of waves, we're really, really going to go into this idea of period and frequency again. And then when you get to the 30 level, they talk about it even more. So you want to be very comfortable with this. Now, according to the definitions that we're going to use, period is typically measured by T, or is symbolized by T, and it's the time required to complete one full rotation of the given circle of a certain radius. And often what I would do is write it as the amount of seconds it takes per given cycle of that overall circle that we're dealing with, or the circle with a certain radius that we're dealing with. Now, frequency is the inverse of this. Frequency, and often the symbol used for frequency is F. It's measured in hertz, and it says if we have a certain amount of hertz, what it measures is how many cycles there are per given second that passes. And so we often write it as cycles per second. Now, I mean, even visually inspecting these two and comparing them side by side, you're looking at them being like, oh, they have an inverse relationship, which is exactly what I want you to highlight. Both of these two things, period and frequency, have an inverse relationship. And the formula that's on your formula sheet is this first one here. So when they say this formula is on your formula sheet, you specifically look under the waves section. So if you want to make a note for yourself, this is under the waves section. And you'll see this formula here. And what you can do is, if you want to get frequency, you just swap frequency and time with one another. And so that gives it that inverse relationship, or where one increases, the other decreases, where one decreases, the other one increases. So we get this nice property of complete inversion. All right. Now, if I look at this piece below here, this is our last note before we go into the practice problems. And so I really want to make this clear for us. On your formula sheet, they give you this specific formula that says that the speed, or the centripetal speed, and I really want you to maybe put this in here too, that it's the VC, because that's how it appears on your formula sheet. The centripetal speed is equal to 2 pi r over t. This equation appears on your formula sheet, and where it's derived from is this first piece here. In kinematics, we dealt with that speed is equal to the change in distance over change in time. Well, on a circle, we know that the change in distance is equal to the given circumference, which is measured by 2 pi r. So I'm going to highlight that, and change in distance is equal to 2 pi r. So tying these things all together, one complete rotation, or one complete lap around a circle, is 2 pi r. Now, in terms of change in time, because we know period is the time it takes to complete one full loop, we're going to symbolize that the change in time is equal to the period, because that should make sense. We have the distance around the circle divided by the time it takes to go around the circle one time, and that should give you the speed it takes to cover that distance. All right. Now, if we go on to, and maybe I'll make a quick note about this one. We're going to deal with this a little bit more in our practice examples, but just even looking at this one here, there is two different ways in which you can write the acceleration equation. And we're going to figure out that there is another equation that deals with, rather than specifically just dealing with velocity and radius, we can also deal with units of pi. Don't worry, we'll go into that specifically, but there's a way to cross compare and say, well, if we know that our force is this, mass times the AC, remember this piece is representative of AC, so I'm just going to circle this and put AC. If we have mass times the AC, and then we know that the 2 pi r, or the circumference over the time, or the period, I should say, is equal to our speed, we can combine those two factors together, and we can substitute this piece in for our given V. We can square that and we can simplify it, and this would be another formula we could derive from here, which would allow us to solve for things like period or mass or radius, just depending on the problem. But again, we won't be too specific about that, and that formula you would more than likely have to derive by combining the equations together here. Okay, now let's go down here to the following. Now, in example 1, we have the following situation where they say a 5-kilogram object is attached to a rope. What is the tension of the rope if the object is traveling at 6 meters per second in a circle with a radius of 4.5? Now, what I always like to do in these problems is just double check, is this kilograms? Yes. Is this meters per second? Yes. Is this meters? Yes. Which means standard units, standard units, standard units. As long as you have them all in standard units, then we don't have to do any sort of conversion before we start. We can go right into this. Now, this is our first exposure to dealing with the classification of these. So we're going to say that our centripetal center-seeking force is equal to, in this problem, they specifically mention that it is tension which is causing the rope to follow this circular pattern. So we're going to write it as Fc, which is equal to Ft. Again, we're not saying it's a first law problem. We're just saying that we're classifying Fc as Ft. This is equal to mass times the centripetal acceleration. Now from here, I'm going to say that Ft is equal to mass times the centripetal acceleration, which is equal to v squared divided by r, and that's on our formula sheet. Now what I'm going to do is just plug in the numbers here. So we get Ft is equal to, our mass is going to be 5 kilograms. So I'll plug that in first with the units, close bracket, our speed, which is 6.0, and in brackets, I'm going to make sure to include that all, just because the squared applies to not only the units, but the actual number itself, divided by the radius, which is 4.50 meters, close bracket. And so therefore, we can write the Ft, or the tension on this cable, as 40 newtons. All right, now, you would look at an answer like that and be like, wait, I thought forces were vector quantities. So is this up? Is it down? Is it left? Is it right? We don't really know, right? That's the whole point, is that in these generic FC problems, or these center-seeking UCM problems, what we're going to notice is that it's really hard to tell where this is in terms of the circles. So generally what you can write is Ft is equal to 40, because in these types of problems, we're going to assume that when we have like a basic setup like this, and it's not vertical UCM and it's not horizontal UCM, if it's just this basic form, we're going to assume that the tension in the cable remains the same at any given point in this circle to maintain this constant speed throughout the circle. Now, as we move forward, I promise that your tension will not always remain the same, especially for lesson 20. We're going to deal with tension varying from the top to the bottom and how that can change speed. But for now, we're making the very broad assumption that the speed stays exactly the same everywhere, and also the tension remains the same in every given key moment. Now, let's deal with a little bit more of an applied problem. If the centripetal force is 80 newtons and it causes a 6 kilogram object to travel in a circle one time every 0.75 seconds, what is the radius of the circle? What is the speed of the circle? Now, right away, I'm looking at this and being like, oh, 0.75, that's your period. When they tell you how long it takes to complete one lap, that's your period, so your t value. They gave us the FC, they gave us the mass. To figure out the radius, we're going to use a different version of our equation. Now, in this, it's not tension, it's not gravity, it's not force of friction. If it's very general like this, what I want you to do is, rather like than what we did in the first one, which is we classified FC as FT, if you can't classify it, just keep it as FC. So when I write this out, I'm going to go FC is equal to mass times the centripetal acceleration. And then I'm going to write this as FC is equal to mass times, on your formula sheet, there's actually two different types of AC. One of them is equal to v squared over r. The other one is the following. We can write this as 4 pi squared times the radius divided by the period squared. That's our other AC on the formula sheet. So depending on what information they give you, you have to read and react accordingly. Now, what we're going to do is isolate this for r, because we want to solve for the radius first and foremost. So I'm going to multiply my t squared up to both sides. That's going to give me the following statement. I have t squared times FC is equal to mass times 4 pi squared times r. Now, continuing this up above here, I'm just going to bring it over here. We have that, and actually I may even be able to divide this just to save a little space and save a little room. I'm going to do one more step here. To get my r alone, I'm going to divide by mass times 4 pi squared to both sides. So this is mass times 4 pi squared. And then this is going to leave me with radius is equal to, and I'm going to make sure I have that in black as well, radius is equal to t squared times FC divided by the mass times 4 pi squared. Now, again, in grade school, typically what you would do is you would make pi like 3.14 to simplify it, but most of your calculators are capable of storing pi or using the pi in its full entirety value, or it's a rational form. So keep it as the whole thing. Don't try to truncate it. Now, this is going to give us a radius, which is equal to the period, which is 0.75 seconds, squared, multiplied by the force, or the centripetal force, which is 80 newtons. So I'm going to make sure I put 80.0. And then divided by the mass, which was 6.00 kg, times 4 pi squared. Remember, we're not going to convert that pi to 3.14. Just keep it as is. Now, when you write the value in here, you're going to get 0.19 meters when you record that value, or when you plug it into your calculator. Now from here, we have a radius, which is a really important piece for calculating the speed. How do we calculate the speed? Quite simple, actually. On your formula sheet, you're given a formula that we discussed earlier in this lesson. Vc, or the centripetal speed, is equal to, And then depending on the information we have, specifically the formula they give you on the formula sheet is 2 pi radius divided by period. And again, you're probably thinking like, what's that 2 pi r? Well, this is the circumference. There we go. And then this one is our period. And because we know now radius and we know the circumference, or we know the radius and the period, I should say, now we can just plug in those values and figure out the speed. Vc is equal to 2 pi r, which is 0.19 meters, divided by the period, which is 0.75 seconds. Therefore, we get a Vc, which is equal to 1.6 meters per second. Now, again, you're like, where is this in the circle? Where is this centripetal speed that we're talking about? Because these circular patterns or these basic problems in uniform circular motion all involve the same tension, the same radius, the same speeds on the outside, at any key interval, we would say that this is 1.6. Or at any key tangency, we would say that the overall centripetal speed is 1.6 meters per second. So no direction. Maybe in the future you might be able to classify direction based on where it is in the problem or where it is in any given specific circumstance. But for our more generalized cases like this, we're going to say Vc equals 1.6. Okay, let's move on to example 3. Example 3 is that we have a force of 45 newtons that causes an object to travel in a circle with a diameter of 7.5 with a frequency of 0.60 hertz. What is the mass of the object? Well, first and foremost, I see a couple issues here. We have diameter, which is 7.5. We don't want diameter, we want radius. And the second one is we have frequency when we actually in these problems want period. Now, as we move into unit D, that might be a little different, but for our case, we definitely want period. So what I'm going to do is first and foremost, for step number 1, let's convert that diameter to radius, and let's convert the frequency to period. So to convert the diameter into radius, radius is equal to diameter over 2, which is equal to 7.50 meters divided by 2, which is equal to 3.75 meters. So it's quite a big radius. Now, our period is, remember, the inverse relationship to the frequency. So I'm going to say t is equal to 1 over f, which is on our formula sheet, which is equal to 1 divided by 0.60 hertz, or hz, which is then equal to, in this case, we get 1.6 repeated. And this is going to be seconds. And if you want to really formalize it, you could be like seconds per cycle, but sometimes they just write it as the seconds because they're implying that that's how long it takes to do one cycle. So if you see me in the future write just 1.6 seconds for period, that's totally fine. Now, beyond this, here's where we have to actually start applying this and say, for step 2, we have to take this information we just found, plug it into our FC. Again, we have no idea if this is tension, friction, or gravitation. So in the generalized cases like this, when you go on to your next step of developing your FC, when you go into your next step of developing FC, you're going to say number 2, and you'll just say FC is equal to MAC. We can't classify it because there is no classification to be had. Now, what this leads us to is that we have an FC, which is equal to, it's jumping all over the place, mass times the acceleration or the centripetal acceleration. Because of the information we have period and radius, and we don't have things like the speed of this object. What we're going to have to figure out is that RAC is going to be the alternative form, 4 pi squared times radius divided by t squared. Okay, our goal is to solve for the mass of the object. So what you could simply do is just divide away this entire term here, or what you could do is multiply and divide. So I'm probably going to do the multiply and divide piece, which would mean I multiply t squared up first and foremost to both sides. This is going to give me that t squared multiplied by fc is equal to m, and I'm going to make that equal a little neater, is equal to m times 4 pi squared r. And then for my last step before I start plugging in numbers, I'm going to divide both sides by the 4 pi squared r. There we go. And this is going to give me a mass, and maybe I'll write it over here just to create some space for us, a mass, which is equal to, and I'm going to get that I have t squared, which in this case, our t was 1.6. So I'm going to throw that in here. 1.6 repeated seconds, and I'm going to square this, multiplied by the centripetal force, which was 45 newtons, and it was given to us in the problem. So 45.0 newtons, divided by, we have 4 pi squared times the radius, which was 3.75 meters. close the bracket. As you can see, every time I do these problems, I include a ton of units and very, very specific calculations. So please include all your units. I mean, the units to this point, or unit A and B, you did a really good job of including units in all your quizzes or unit tests or practice problems. So just continue that, because as you go further into Physics 30, I mean, it's going to have a huge payoff. So I'd make sure you do that. Now, our mass is going to be equal to, if I summarize this, I get the following. Mass is equal to 0.84. And of course, we always measure our mass in our standardized units of kilograms. So that will be important to put there. Okay, now we got one last problem, and it deals with the following. It says, if an object rotates around a circle with a radius of 4.75, or I should just more blankly put it as, an object rotates around a circle with a radius of 4.75. If the object completes 15 cycles in 35 seconds, what is the centripetal acceleration? Okay, interesting. Again, no sort of classification here, just some information that deals with overall uniform circular motion, plugging it in. Now, right away, I want to identify the following. They give us a radius, so that's good. And then they tell us it completes 15 cycles in 35 seconds. Now, I'm going to give you something that a lot of students actually did in class that I saw, and it was this. Because of the order in which they gave it to students, 15 cycles per second, a lot of students said, oh, that's frequency, because frequency is the amount of cycles per second. So they went, frequency is equal to 15 cycles divided by the 35 seconds, and they calculated that given frequency. Now, here's where I would challenge you. What is the point in doing this if you know you just have to inverse it right after? We may as well just say, well, if frequency isn't going to help us within these sorts of problems and period is more important, I would rather you go period is equal to, and then just take the 35 seconds or that total time, divide it by the amount of rotations or the amount of cycles, and then automatically you don't have to inverse this, and rather you can just say it's 2.3 repeated, and this would be seconds per cycle. Now again, seconds per cycle, that might be a little longer. Sometimes you'll just see me write 2.3 seconds or however many seconds. Now that I know my period and I was able to figure that out from that information that and put it in a relevant term rather than writing it as frequency, now I have the period that I need, I'm going to go directly to our AC formula. AC, or the centripetal acceleration, is equal to, we always know that we're going to have to choose between one form and the next. So we could either say it's v squared over r, or our other form is going to be 4 pi squared r divided by t squared. Now, on surface value, you're like, well, we weren't given a speed, so this formula doesn't apply to us. It's not important. In fact, we're going to say that our AC is equal to 4 pi squared over r times over t squared, because we're able to find our period. We do have our radius, but we definitely don't have a speed, so we don't want to go that direction. AC is equal to 4 pi squared r, which was equal to 4.75 meters, divided by the t squared, which was 2.3 repeated. And try to put as many decimal places as you can there, because you really want to make sure that you get the most accurate value. And if you just truncate it to 2.3 right away, your answer may be different than other people around you. Now, the centripetal acceleration is equal to, for this piece, we get 34.4 meters per second squared, because we got our 3 significant digits. Excellent, there's our answer. And let's just double check it's 3 significant. I was pretty sure. It looks like it's only 2. So realistically, if you did 34.4, that's okay. If you also did this, so I'm going to just zoom in here again. If you made this 34 meters per second squared, because you noticed that the time and the overall cycles were both in 2 significant digits, then that would be okay too. So just be careful of how many digits they ask for, because it could be 2, it could be 3, it could be realistically whatever they would like it to be. All right, now here's where you want to go on to your work problems here. So I definitely recommend getting some practice with this. In this lesson 19, the big thing is revisit the formulas, revisit the terminology. What is period? What is frequency? And then remember that the tangential velocity will always remain the same. The F net, which is our FC, points towards the center and is that center-seeking force that is causing that continuous directional change. And lastly, just make sure you're careful with your units along the way, because I know sometimes they'll try to throw a wrench in this and be like, oh, if I give you things like in grams, or if I give you things in, what would be an example maybe from something above, diameter, they give you the frequency. They try to give you these things that throw you off, but you need to be very careful with that. Lastly, you have a couple formulas on your sheet. namely ACs and VCs, make sure you use those appropriately. And remember, a simple memorization tactic could be unit C, we're dealing with things with the subscript of C, and that will help you guide your studying here. All right, good luck with the practice.